so I will present economics-inspired neural networks for stabilizing adiabatic model transformations. So we changed the title a bit because what we are doing is not really homotopies. Previously we called homotopies, but as Felix and Fedor told us, these are not homotopies. So we corrected this. And it's joint work with Azinovic, who is extremely talented and teaching me a lot on this project. And he is starting his PhD in Zurich in the fall. And yeah, so this is going to be my job market paper. Today I will focus on the methodological part. And I'm really glad I can present it here because this is the perfect place to present this.
You will tell us what adiabatic means.
Right, yeah, that's what I will tell you. This is also a risky title, but it's less wrong than homotopies. Even though it's slightly wrong. But you will see exactly what I mean. So what is our starting point? So there is a class of models where we have aggregate risk in multiple assets. And these models quickly become challenging to solve. Why are they challenging to solve? Because on the one hand, we want risk, we cannot linearize. And on the other hand, if you have some kinks or if you have some strong nonlinearities, perturbation methods might not be able to do it. And then if you have multiple assets and many agents, we also very quickly get a high-dimensional state space. And hence grid-based methods run out of steam. So this is something what we kind of saw throughout this conference. And then there is a class of models which and I'm very happy to present here in front of so many people that basically started this literature. And I'm going to focus on a paper which we wrote before with Simon and Luca Gegau, which we call deep equilibrium nets. In these kind of methods, we make use of neural networks because we are very good, because neural networks are good at dealing with high-dimensional state spaces. But then there are some things, I think, which collectively we still want to improve and move a bit forward. And the two kind of things which were, at least for me, tricky to do were portfolio choice. That's one thing we want to address. And the other thing we want to deal with is market clearing conditions. These are the two things. And so how do we do this? We present two complementary basically extensions. One is market clearing layers. What do I mean with market clearing layers? With market clearing layers, I mean neural network architectures which then by design only predict policies which are consistent with market clearing. And the second innovation is what I call adiabatic model transformation, which means that we start solving an easy model and then smoothly go to solving a hard model, thus at every step in time, having a very good starting point. And I should also point out this idea has been also done in other contexts. So for example, Hanno in his paper, they start with a representative agent solution and then they go to heterogeneous agents. We do something similar, but we go directly for portfolio choice, meaning we start from a one asset model and then we show exactly how to go to a many asset model. And sometimes you just want to know the basic idea, but it turns out sometimes also the details matter to make it work. So I'm gonna go in great detail on those 2 points. In order to understand what we are adding, I first have to take a step back and explain the previous paper, which we call deep equilibrium nets, a little bit, because you're really building on top of it and taking it a step further. For those of you who already listened to Simon or me, this is a little bit of a repetition, but I try to go quickly so that. But if you have questions, you should always ask. I want to be clear. So, what is the basic idea in deep equilibrium nets? And there are other papers who work in a similar vein. I'm just choosing mine because that's the one I know the best, and that's my starting point. So what's the idea? So say we have a state of the economy X. For example, you can think of capital and the exogenous shock in a stochastic growth model. Often we can write the equilibrium conditions for a functional rational expectations equilibrium as a set of conditions. let's G call the set of equilibrium conditions. What are those? There's a set of equations that, given the state of the economy and the policy function, they have to evaluate to 0. You can think, for example, as the set of Euler equations. And if I give you a state and I give you a policy, when you plug it in on the left and you plug it in on the right, this condition should evaluate to 0. So we know that the functions we look for, the true equilibrium policy functions f, are implicitly defined like this. And the idea then is to take a neural network to approximate this function. N rho denotes a neural network with parameters rho. And we hope that it's close to we hope that we can get it to approximate those equilibrium functions f. How can we do this? Generally, this would be hard to do because in standard deep learning, we would need kind of the true f, and then we would try in a supervised way to train the neural network to predict the true f. But here we don't know the true f. And the key insight here is that even though we don't know the true f, we can still write down a cost function which tells us how good is our approximation. Because we know that for the true equilibrium functions, these conditions G have to evaluate to 0. We can plug in the neural network there. We can just see how far are we from 0 and how do we have to change the neural network to get this closer to 0. And that's how we proceed.
Quick question.
Yes.
So this idiosyncratic and aggregate shocks or only aggregate shocks?
Here, for this talk, think only about aggregate shocks.
Aggregate shocks.
For this talk. I'm looking at OG models with aggregate shocks, but you can do this also with idiosyncratic shocks. But for this talk, let's focus on what is on the slides, because otherwise I'm gonna go. Okay. All right. So we can, let me quickly repeat. So we have this implicit loss function, which tells us if we take a given policy, are the equilibrium conditions satisfied? We've also seen similar notions yesterday. The next question then is, where do we want these conditions to be satisfied? In principle, we want it to be satisfied everywhere for all possible x. But in practice, and especially in high dimensions, everywhere is not possible. So what do we really want? We really want these conditions to be satisfied where it matters, which is the ergodic set of states of the economy. And how can we get there? The way we do it is we start with a given policy encoded by the neural network, which of course in the beginning of training is not correct. Then we simulate the model from this policy, we collect these states, and then on those states, we evaluate the equilibrium conditions, then we check how much are they not satisfied. They are 10 to the 5 not satisfied. That's very bad. But how do we have to adjust now our neural network to decrease it? We adjust it in that direction. Then we have a new policy now because we adjusted the neural network policies in order to reduce that error. Now with the new policies, we can simulate new states. That will be slightly different states because on the one hand, there is randomness. On the other hand, we have a new policy now. Then we plug these new states into the conditions. Now maybe they are just violated by 10 to the 4. And we repeat this game until hopefully we are coming close enough to fulfilling those equilibrium conditions. That's kind of the starting point, the basic idea. This so far has been a little bit abstract maybe, if you haven't worked with this yet. So I want to introduce a simple model which I will use for concreteness to go step by step of what we are doing. And the simple model I'm introducing is an overlapping generation model with capital and bond and 32 age groups. On the production side, we have a standard representative firm, which produces from capital and labor. There's TFP, which is stochastic. The firm pays a competitive wage and a competitive return on capital. We assume that the TFP shock also affects depreciation. That's not necessary, but it creates a bit more action. And we put in borrowing constraints. So B will denote the bond holdings of H group A. K is the capital holdings of H group H. Sorry, of H group H. And we, for simplicity, I just put them to 0. and we assume that the bond is in net supply B, which is constant, and there's aggregate capital. The households, they receive a labor endowment, which they provide inelastically. It will depend on the age. There will be a life cycle. We will not have death, so we will assume that people live always the whole 32 periods, and then when they become 32, they know that tomorrow they are dead, and we also assume they eat up everything before they die. And they know you're dead tomorrow because of the adjustment costs. This is kind of an assumption, because in principle, if you would have super high capital, you wouldn't want to adjust all the way down to zero. But for reasonable calibrations, this is not a strong assumption at all. It's basically no assumption. And they maximize their lifetime utility with time temporal expected utility and CI Bernoulli utility. In this, so is it? Let me first ask: is this setup clear? It's always good because I have to get to the model below 10 minutes. That's the rule, and you check the time. That's why I can ask you if it's clear, because I made the time. So here we got the model. All right. So if I now want to think about this model in terms of the equilibrium conditions G, the state X, the policy functions F, how would that look like? So what are the equilibrium conditions which characterize the equilibrium in this economy? Number one, we have market clearing conditions. We have market clearing condition for capital. This one is not red because it's trivial. We can ensure basically that this is always satisfied by basically just defining aggregate capital as the sum of the capital the households hold, so then capital market clearing will be satisfied. The other one is the bond market clearing. And remember, here I'm still talking about the basic deep equilibrium nets. How would they do it? They, meaning also me, but so me, the old me. So and there we might have a market clearing error, and I will denote it by epsilon b. So that's something we have to make sure holds that there's so. And then we have the optimality conditions for the firm. Again, those are true. We can trivially satisfy them by just defining the wage and defining return, reading it off those two equations. And then we have household optimality conditions. So remember, we have 32 generations, but the last one is dead tomorrow. So 31 of those generations have to choose how much capital to save for the next period and how much bond to save for the next period. And because there are borrowing constraints, they will generally do this. The way they do this will be characterized by a condition of, by a set of Karush-Kuntake conditions. So we have 31 for capital, we have 31 for bonds, and these are now inequality constraints. So this doesn't directly fit. I mean, we could yeah. Okay. So then one question is what is a convenient way to transform this Karush-Kuntake conditions into the kind of GFX way of writing things, and it turns out that making use of the Fischer-Burmeister function, there are also other functions we could use. So the Fischer-Burmeister function is defined on the bottom, and it's a function that it's zero exactly if A and B are both non-negative, and the product of those two is zero. So we can encode for each age group the equilibrium condition for each asset as basically one equality constraint. That's just the nature of the Fischer-Burmeister equation. If you want, you can equivalently think, or maybe not equivalently, but you can also think about those conditions. So the equilibrium conditions are market clearing, firm optimization, and then 2 times 31 optimality conditions for the asset choice. Now let's put this into the deep equilibrium framework. Yes.
Make sure I understand the Euler equation for capital. So I buy the capital and then I'm exposed to the depreciation risk.
Right.
But there's no price there. I'm not exposed to price risk.
Right. So
or you know there's an adjustment cost on capital.
You would have a price risk if there would be an adjustment cost on aggregate capital.
Yeah.
you could model like a financial intermediary.
Right.
I will do this later. I'm confident I will get to it. But that wouldn't, then you would have a Q next to the 1 minus delta.
Yeah.
You would have a QT plus 1, and you would have a QT on the denominator there, right?
Yes, yes.
So, but essentially it would look very similar, just you would have the Q in there. And this Q, if you would model the financial intermediary way, this would also be a closed form Q, like a trivial Q, right? But I will show you later. So this is the simple model. And actually, you may realize that now it's a simple model. It's also because all the progress we made, because this still has 32 times 2 dimensional state space with aggregate shocks. And a while ago, this was not a simple model. So let's think about what is the state of the economy. It's the shock, the distribution of capital across households. I'm making a notation simplification here. This is not really 32 dimensions because we know that the first agent always wakes up with 0. So in fact will be 31, but I want to keep notation clean. Then this is the distribution of bond holdings. What are the equilibrium policies you look for? It's the how much the asset choice for capital, the asset choice for the bond, and the price for the bond. How would we approximate those policy functions? By a neural network which predicts capital, bond, and price for each age group, and the price, of course, is for all age groups. Then what would the loss function be? It would be the Euler equation errors on capital for each age group, the Euler equation errors for bond on each age group, and a market clearing condition. So that would be how we did it literally in the previous paper. Now let's take this as a starting point. So what would I like to improve? So on the one hand, now this one single loss function includes all equilibrium conditions. Generally, this can be many different conditions in also many different units. So implicitly, the neural network has to make trade-offs between how much do I satisfy the agent's first order condition versus how much do I satisfy the market clearing condition. Because in practice, none of them will be exactly satisfied. This, on the one hand, this may make you feel like, okay, how should I weigh those? When should I consider it solved? Which one has to be more precise than the other? But on the other hand, it also makes just the loss value that you get much harder to interpret, because now you have to think, I have not only one error, I have like 10 errors, and in principle, I need to study each of those. And on the other hand, I think it's also a very crucial point. If market clearing is not satisfied and I'm simulating from the policy, then my trading states I'm getting now are also not consistent with market clearing. And then if, for example, if I wake up with too much assets today, then the correct policy, the equilibrium policy, would also make me have too much assets tomorrow. So not even every update might, strictly speaking, go in the right direction. The third point is, if you know that market clearing holds, why should we have the neural network learn it if you already know it? And for example, Uchen's paper and Jesus' paper, they make also the same point regarding symmetry. If there's something of the economics we know, why would the neural networks have to learn it? Can we not just put it in? And that's exactly what we are doing. So how do we ensure that the neural network predictions are always consistent with market clearing? So we're now saying that the neural network doesn't predict directly B hat, but something intermediate B tilde. Then we apply transformation M to the B theta such that for the B hat that we get out of it, they are always consistent with market clearing. And then our final prediction, which we put out, is now a prediction of policies which are consistent with market clearing by design, because we did apply this transformation. What does it give me for the loss function? It gives me for the loss function that now I don't need this term, because now it's always satisfied, so I can get rid of this term, and now all errors I have can be interpreted as consumption errors of the households. What's the two advantages? This is easier to interpret, number one. Number two, if I now simulate from this policy, it will always be consistent with market clearing. Some details, so what should this transformation be? Of course, you can come up with many different ways. to do it. The simplest one, which is also the one we run with, is to just literally sum up the excess demand implied by those originally predicted policies B tilde. Then you know, and then you adjust equally each household, so that the adjusted policies are now consistent with market clearing. There are different versions of this. For example, if you would have a mass distribution, you would not adjust. You would need to take care of the adjustment, such that if one household has a larger mass, that you would adjust that the weighted adjustment would still be zero, and would still be correct. And why do we do this? We do this because we thought of a desired adjustment as such. We wanted to minimize basically the adjustment we have to do, such that the result is consistent with market clearing. And this is a quadratic program. And it turns out that this very simple quadratic program has this very explicit closed form solution, which makes it extremely easy and fast to implement. And there are some downsides to this. And the first downside is that previously, with, for example, using a soft plus activation function in the outside layer, we could have ensured that the boring constraints are always, do I have a question? Okay, that the boring constraints are always exactly satisfied. But now, if you would subtract something, then potentially they could be violated. So instead, we can write down a different problem, where we are also demanding that all xt plus 1 are consistent with the boring constraint. That's a harder quadratic program, which you can still code up and you can still differentiate through it. And that's, we tried it in the paper, but those quadratic optimizers are implemented in deep learning libraries like JAX. And the way you get the derivative is basically through the implicit function theorem. But the problem is, so far, that this was very slow. So the benefit we got from directly enforcing the boring constraint didn't pay off compared to the runtime punishment we got. Another issue is if we set people on the constraint by some kind of max, we lose the signal from the loss back to the policy for those households which are wrongfully constrained, because we took a max. And also the signal can be restored. We show away in the paper. So, but these are details. So, so this is what we're doing. Very simple adjustment, very easy to compute, and you get those benefits. And now, what's the second point we're doing? The second point is an observation that single asset models, at least from my experience, but I have a feeling it's not only my experience, single asset models are kind of easy to solve with deep learning. But one reason we do deep learning is because we want global solution methods, where we need global solution methods, exactly with many assets. But then, many asset models are kind of hard. Why are they so hard? Well, I think this is the reason. Portfolio choice is only pinned down once you have a pretty low error in the equilibrium condition. Getting your consumption function right, looking roughly right, is kind of easy. You get this quickly. But getting the portfolio choice right, how much bond do I buy, how much capital I buy, this is much harder, and this requires a quite low error in equilibrium conditions. So I could write down to you, so I could show you solutions which have an all equation error of on average 5%, but they have very different portfolio choice. But if we need those low errors to pin down the portfolio choice, then how do we get there? Especially in a simulation-based solution, if we didn't pin down the different policies correctly, and we're simulating from this very weird policies which basically cannot distinguish between capital and bond, then we're also not getting training states which are easy to train on. So what do? We realize that an n asset model always nests an n-1 asset model. In this example, if I just multiply all the bond predictions by 0, I set the net supply of the bond to 0, and I put the boring constraint to 0, then this model now becomes a model with only capital. And then we can solve the capital only model. And now we have a very good starting point for a model which has a little bit of bond. But before we turn on the bond, remember, so the whole key is that in order to get the portfolio choice right, the error needs to remain low. So now we have a very low error in the capital only model. We want to make sure that when we introduce the bond, the error remains low. So before we just blindly turn on, because remember, the price in SOFR was irrelevant. So this prediction is a random variable. So before we introduce the bond, we train the bond price, and we can get a closed form solution for this bond price. I'll go into more detail later. And then we slowly introduce a small amount of bond into the economy, and the economy with only capital is an extremely good starting point for the economy with a little bit of bond. And then we go ahead and we slowly increase the amount of bond slowly enough, going up here. Every time we have a very good starting point for the next kind of model we're solving, and the error always remains low, we're always able to pin down the portfolio choice. And that's why so as you ask, what is adiabatic? So adiabatic is a physics term, and what it means is, in physics, you transform a system slowly enough so that at every step, it's in the ground state. So what is the ground state? Ground state is the energy minimizing state, which means basically at every step, it's in equilibrium. What do I mean here? I transform the system slowly enough that every time I get low errors in my equilibrium conditions, because that way I ensure that I'm not getting into this region where my portfolio choice is just not pinned down. Yes, Simon, please.
Can I say, or can one say that this is sort of a very expensive way to pre-train the model?
Right, totally. Expensive, I'm not so sure. Because do you want to train your model once and it works, or do you want to train it a million times until it works? If you think, you know, like, and also expensive, you have to think about human time. If I have to fiddle, my bottleneck is often computer, but mostly it's manual time. So if I have to fiddle with, you know, whatever parameters until it, thank God, runs, then that takes a lot of manual time. I want something, and this is what I meant with pain points. We made a lot of progress, but there are some things which we still haven't, like, which still didn't fully spark joy, which we just have to keep making progress. And one of those things is that for many asset models, definitely it's fair to say it didn't run out of the box. Maybe with 2 assets, okay, 3, good luck. That's also why I was very impressed by your 3 assets yesterday. Yes.
Can you give us a sense of how slowly you have to increase speed?
That's a very good question. Right. So let me show you in detail.
Right.
My answer is going to be, depending on your model, you have to do it so slow that you are never going into the region where you cannot do portfolio choice. And how much error you need to do this really depends on your model. Like, and I cannot tell you, but so for my model, if the error goes to 10 to the minus 5.8, I'm fine. If the loss function would go to 10 to the minus 4, which means 1% mean Euler equation error, it's over. It's game over. The policies will get crazy, and then the simulation will get crazy, and then, you know, I basically restart training. It might still work out, but once you get these very high errors, you're losing a lot also of what you already trained.
Yep, just to make sure I understand correctly, you don't do any parameter freezing. You just use the previous solution as your initialized price for the use.
Correct.
Right?
Correct. And I like in the details also other things, for example, the state of your optimizer add-in. I would also not restart this.
You reset this.
No, I do not reset it. I want to reset as little as possible so that I'm going smoothly. Because if you reset add-in, you might get a spike up, and this is what I want to avoid.
Thanks.
Okay, so what does it mean? Let's be concrete, let's go step by step. This is not a quantitative model. I just put some parameters. I didn't even call it calibration because I just put them there. I put here 88 groups, but in reality, these are just 32. But the main point holds, and so these are some parameters. Here, because I don't want to model a government, but I want to get some life cycle notion, I just assume that the exogenous supplied labor endowment is dropping a lot once you reach your retirement age, which is about 60. So, how do we start? Step one. Step one, solve the single asset model. How do you do this? You set the boring constraint to 0, you set the net supply to 0, you put a mask here, which is 0 pre-multiplied in these predictions, and then also the final predictions will all be 0. And in your loss function, you now don't care about the bond optimization, you only care about the capital optimization. This is a capital only model nested in the capital and bond model. We solve this. This takes 3 minutes on a T4 GPU for this particular model, and the way I coded it. Could it be improved? Probably yes. So what do you see here? I just want to introduce this plot because I will show you the same plots later, and then they will be more important. So here's the loss function during the training. We just see it goes down. If I would decrease the learning rate, I typically can go to the lower envelope of this pattern you see here. But because this is just a capital only model, it was kind of good enough. Here I show you the asset holdings on a similar part of the economy. The mean is always a solid line, and then just to get an idea how much variation there is in the simulation, I'm also showing you the min and the max. This is a very important thing. This shows how much are the equilibrium conditions not satisfied. So on the average here, it's 0.2%, and the 99 percentile is going up to roughly 1%. In this model, we could get it down to 10 to the minus 7, 8 if we were a bit more patient. Here I'm showing you separately the left-hand side of the Euler equation and the right-hand side of the Euler equation. And I'm showing you just the mean in order to not give you too many lines. And we can see that where households are unconstrained, these lines touch. And where they are constrained, one is above the other because they can't borrow to equalize them. And here, here you cannot see a lot, but I mean, here you can see, but later in what I will show you cannot. So here I'm showing you the wedge, which is just the difference between the right-hand side of the Euler equation and the left-hand side of the Euler equation, the way you are used to it. And so here we see that when they are not constrained, this is 0, and when they are constrained, it goes up. Okay, this is step 1. Now, what is step 2? Pre-train the price. Yes?
I asked a question regarding the previous slide.
Sure.
Is it possible to achieve a longer, maybe 10 times or 100 times lower than you can here?
It depends. In this model, I do not think you can get within reasonable time to 10 to the minus 10. I don't think so. And I think this is a big limitation. And it's not only true in the econ model, also in the PDE literature. What you find is that, we can go high dimensional very easy, but with the traditional method, you can get the error as low as you want. And unless you use very easy models, so the notebooks I show you, you can go basically to machine precision. But these are easy models. On hard models, I have not seen anybody to go to 10 to the minus 10. I just haven't seen it.
What is the reason? Is it numerical precision of that?
I was thinking about this a lot. I tried it in a non-rigorous way. They're increasing the precision too much. Also, it becomes much slower, not factor 2 slower. It becomes factor 20 slower. So I can't say, but I would say that's not a me issue, that's a deep learning issue. We just have to find out what models we can deal with within this framework. And this is a very important point. Now we want to add the bond, but we want to make sure that when we add it, our loss function does not jump up. So we want to make sure we have the correct price. And it turns out that we can get a closed form solution to train the price in a supervised way. What do I mean? And this is, I think this point is general beyond the exact deep equilibrium nets way I'm doing it. So we can basically read out the price from the Euler equation of the households. And then, of course, in general, because the bond is not in the economy yet, they will be different. But the marginal agent who would price the bond, that would introduce a little bit of bond, would be exactly the one who would basically obtain the biggest price here. So I can get a price by just really solving all the Euler equations for the implied bond price and taking the max. And this is exactly the correct price in what I call the zero liquidity limit. Now I have a supervised objective to train the price. Supervised learning is comparatively very easy. So this gives me a surefire way to get the price before I turn on the bond. And because the policies are still at zero, the rest of the model conditions will not be influenced. So this is also an important point. This is why I call it supervised here. We do not want that now the capital policies adjust to reduce this error. We really want only the price to learn to predict this. And notice, because you have aggregate shocks, this is not a point. This is a function. We are learning a function. And to ensure that we just train the price and not the policies, we can do a stop gradient around this term. That way we are sure that only the price adjusts. Let's do this. How does it look like? Here I know the top plots are unchanged. Here I'm showing you the left side and the right side for the bond now. And here I'm showing you the difference. You can see all households would be constrained except for one. The one who's about to retire. Why this one? Because with that price, with the zero liquidity price, he's the one who would buy it. And the price would always be such that exactly his Euler equation holds. All right. So now, and this is why this is a very good starting point. And notice that here it went up a bit, but this is not a problem because this just went up because the price was not right. But because the price is nicely separated out of the policies, this will not screw up the policies. That's why we need to stop gradient. If you wouldn't have the stop gradient around this term, this point may screw up your policies in order to reduce the price error. Okay, so this works. And now it turns out that we have a very good starting point to put a little bit supply. And that's why I have to pre-multiply this with a small number. Because so far, these are just random numbers. So if I would just turn it on again, there might be negative consumption, I get huge errors. That's not what I want. So I have to make sure that I start close enough to the solution. And now I turn on also the bond-Euler equation, because now there's a bond. And now here I'm showing you the loss across the adiabatic steps. So every time I increase the supply of bond, I'm showing you a loss here. Here you see both assets. Here you see a tiny, because I already put a tiny amount of bond. So you can see here, this is the consumption function. If you are kind of bored, you can just look how this consumption function changes if you increase supply, and you can guess how it would do it. Here this is the loss within one homotopy step. These are the two errors. Key, they should never get too high. So let me put a little bit more. It went up. I mean, almost by construction, it has to go up because for constrained households, the error is zero. So if you are constrained people, the error will go up a bit, but it doesn't go up too much. So we're still in okay-ish region, at least for this model. Then we keep going, 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 and it gets bigger, it gets bigger, it gets bigger. You can see it kind of worked out. And so after we are done with this procedure, what I typically do is I train a few more steps just with the final policy without adjusting the model anymore, just to give it like really awesome to make sure that the algorithmic set I'm having is really totally in line with everything. So we're training this here, and that's what we get, and the errors are reasonably low. If you look at the consumption function, you can see it's much steeper now. Okay, so this was the most important part of my talk. So if you have questions? Yes.
Often in those models, we just replace one of the policy functions, okay, by the market clearing condition. So we have one less unknown policy function. What is the advantage of adjustment for market clearing?
Okay, right. I think that's a good point. This goes to the question like, how do we adjust? One way to adjust the policies to have this what I call the M function transformation is to say, well, everybody just does what he wants to do, and the last poor agent just has to choose the residual demand. I don't have a rigorous proof also because not even a rigorous proof. I don't even have a rigorous numerical study for you, but we did play around with it, and my intuition is that what you are suggesting would be very asymmetric. Like you would basically load all the errors to one pool agent. And like in the overlapping generation model, you would like kind of screw up. Like one Euler equation would have to carry all the error for all the edge groups, and that worked less good. We also tried, of course, you could also, instead of subtracting, you could divide by the supply to scale it down. We also found, in our experience, it also worked less well. And that's why we went back and we thought, okay, but how do we want it to look? What would be the adjustment we really would like to have? And I think this is an intuitive way to describe the adjustment I would like to have. Because training neural networks is a bit tricky, and you do something very complicated, it might make it more tricky. And yeah, just the numerical studies with deep learning are very, because it's stochastic and you would need to optimize the hyperparameters, it's just very hard to do, so that's why I didn't do it. From my very limited trying, this is what performed best, but you know, it could be that I just tried the wrong learning rate. And now I want to show you something, because one thing about this method, no,
41 minutes.
no, I mean there's still 1 minute. So I want to show you something more interesting. No, I have shown this. We coded all night so that I can show you this. All right. So now we introduce something more interesting. When we have new methods, we also want to do new economics. So what do? You do a stochastic process on the size of the incoming cohort. It's an AR2 process. Then we add land as a third asset. This increases our state. So this increases our state space by age because I have to keep track of the mass distribution across age groups. Then I have to put land, then we put adjustment utility, and then I put adjustment cost and aggregate capital, which gives me an implicit capital price. In this model, what is the state space? 1, 2, 3, 4 times age. We choose 24. That's a high-dimensional state space. Now we have to predict more stuff. We have to predict value functions. We have to predict true prices. We have to predict also land savings. And then we have this additional terms in the last function. Here, we do not need these two because we took care with our architecture. And then, just to show you how does the mass distribution across households look like, we have just different prioritizations. So sometimes you have lots of old people, sometimes you have a lot of young people. That really changes the economics of your model. So this is not a trivial extension of the state space. This state matters. It would be really hard to process with this. So if you think about the demographic typical curve that you see, if you want to see something very extreme, you look at Armenia. They have a very crazy, but this even for the US, plus minus 10% is not crazy. We do the same thing, we put bonds, we put land, it works just fine. Oh, here it went up a bit, but only to minus 6.6, then it went back down. So it would have gone up more, we would be screwed. Thank you very much.